Hello there, I'm Mr. Math Guy, and today we're going to take a look, a 10-minute video on sectors and segments of circles. Let's start by taking a look at the definition of both of these words, and then looking at a visual of the definition. So the first one, a sector, it is the region bounded by two radii and the intercepted arc. So it would look like this if I can draw it a little bit here. If I have a radius here and maybe a radius here, so I have the two radii, and then its intercepted arc is this arc right here. I'm trying to stay on the circle best I can. Alright, it's the area that's bounded by that, so it would be all of this area. This is what a sector is. So if you're thinking about it as maybe a food, it's a slice of pizza. All right? It's a slice of pizza. It's part of the circle. Now, a segment, on the other hand, is the region bounded by a chord and its intercepted arc. So if you have a chord, let me try to redo that. If I have a chord runs from maybe here to here, and you got its intercepted arc, I'm trying to start on that circle there, and its region, this would be what a segment of a circle is. So you can kind of see the difference. Alright, sectors are bounded by the two radii and its intercepted arc, while a segment is bounded by a chord and its intercepted arc. So by definition, a semicircle is a segment of a circle, because a semicircle is a half of a circle, which is a diameter. A diameter is a special type of chord, so a semicircle would be a segment of a circle. Now let's look at in detail here, more detail at sectors and some things that we can learn from them. The first thing that we want to learn when we look at sectors is how to find the length of the intercepted arc. Probably we know what the degree is. For example, if I know this central angle is 80 degrees, then I know that its intercepted arc is also 80 degrees. But that doesn't tell me the length of the arc. What I want to know is how long it is from here to here, not the degree that it is. I want to know, because we know around a circle is 360 degrees, so this is 80 out of 360 parts, but what I want to figure out is the length of it. If I were able to stretch this out into a line, how long would the intercepted arc be? Well, there's a formula for that. It's going to be L, that's what we are representing to be the length of the arc. L is going to be, well, the circumference of the circle, 2 pi r times theta divided by 360, with theta being the central angle. All right. Now, there's some things that can reduce here. This 2 and this reduce. So what we get then really is L is equal to pi times the radius times theta, or the central angle, all divided by 180. That would be the length of the intercepted arc. Now that's going to be vital for us for the next thing that we want to take a look at. So let's say that I have a circle C here, and I have two radii that form an angle there, and that angle is 134 degrees. And let's say the length of the radii is 12 units. What would be the arc length, the intercepted arc length? So I'm asking, what is the distance from here all the way around to here? How long is it around there? Now we could figure out the circumference of a circle is 2 pi r, but we don't need the whole thing around. We just need from this part to this part. So we just use our little formula and we say, well, L is going to be equal to pi times the radius, which is 12, times 134, all divided by 180. That's going to give us 1,608 pi over 180, and we can simply reduce that and get 134 pi over 15. Now, let's just see if that kind of makes sense. And the way that I want to do that is, let's take a look at the circumference of the circle. So circumference is 2 pi r. So circumference then of this one would be 2 times the 12 times pi. So the circumference would be 24 pi. Now, when you compare it to this one right here, 134 divided by 15 is 8.93 repeating pi, right? Now, this one should be smaller than this one because this is the distance around the whole thing. This is just distance, think. Now, if this was 180 degrees, it'd be a semicircle. And 180 degrees would be 12 pi. Well, this is kind of close to 180 degrees, and that's why it's kind of close to 12 pi, 8.93. All right, so this is just finding the distance or the length of the intercepted arc. So this is the main thing that you need to know right here. L equals pi r theta divided by 180. The next thing that I want to take a look at when we're talking about sectors is the area. How would you find the area of that sector? Well, we know the area of a circle is pi r squared. This is just going to be part of that. So our area is going to include the pi r squared, but it's going to also take into account what that central angle is, so theta divided by 360. What part of the circle is it? That's what the theta over 360 is. So to figure out the area of a problem like this, with the radius of 12 and the central angle being 80, you just simply plug things into your formula. So you got pi times r squared, so r is 12. 12 squared is 144 times 80 pi divided by 360. And when you multiply that out and divide by 360, you get your answer is 32 pi. Remember, area is always in square units. So 32 pi square units. Now let's compare that with the area of this circle. We should know the area would be a lot larger. So the radius is 12. So the area of the entire circle is 144 squared units. Now, this number should be larger than that one, and it is. It's quite a bit larger because there's a lot more part of the white that's not included. The white area is a lot bigger than just the blue shaded area. All right, so this is how you find the area of a sector. Right here, this is what you need to know. So we have the length of the intercepted arc and the area of a sector. Now, let's take a look at one final thing, and that is how to find the area of a segment. To find the area of a segment, there's no formula here. Basically, what we have to know is we have to take a look at the intercepted, or excuse me, the radii, so from here to here, and from here to here. And what we would do is we would find the area of this sector using our formula for area of sector. And then once we found the area of the whole sector, then we would subtract the area of this triangle. Sorry, messed up here. We would subtract the area of this triangle, this part right here that I'm shading in blue really quickly, and we would do that because this is A equals 1/2 base times height. So there's no real formula here. We just have to use a couple of geometric principles here. We have to do the area of a sector and then subtract it from the area of the triangle that is formed here. Alright, so that is a quick session on sectors and segments of circles. Hope you enjoyed it. God bless.